Mathematical proofs is central to mathematics. So if you can prove something, then you can put your faith in it. That you know that, okay, this is true. Once and for all, I have proven it logically to be true. So then you can safely use it to build up your mathematics. So a central part, and then also it's important to our understanding. When you prove something, you understand better why the theorem holds. Just accepting proof without seeing a proof, it hinders a little bit your development in mathematics. So, but there are different types of proofs and different ways of proving, really. For a mathematician at research level, they think of proof in one way, more algebraic or formal proofs. Whilst if you go to the elementary school, they mean a different thing. And if you go to kids outside schools, if you talk about proof in society in general, it means maybe something else. Maybe something that just a convincing argument or something. So it depends also on the context. But we will now focus mainly on proof in teacher education and also with an eye on schools. So maybe not the most stringent, but still up there in the stringent part of mathematics. Then we can talk about different kinds of proofs. We can talk, and some of them, if you take at the top level mathematicians and research in mathematics, some of them wouldn't consider some of them we are taking up here now as real proof, but maybe as proof sketches or something. But if you go to school and teacher education, you can talk about different types of proof. So you have, for example, formal proofs or algebraic proofs. Then you are using symbols or algebraic expressions and calculations to show your results. So it's manipulating strings of logical symbols or counting algebraically. So for example, the formal or algebraic proof could be, for example, if I want to prove that the sum of two even numbers is even, then I write A is 2 times an integer, and then B is also 2 times another integer. Then I prove that the sum of these by working with this and so on. We have gone through proofs of these types earlier in number theory, so I can put a link on that up here in I. That's the kind of proof we're talking about, formal algebraic proof. Then another type of proof we can talk about is geometric or visual proofs. And that are proofs that are based on figures. You argue from a figure, that you realize things are true just by looking at figures, or maybe combining with other types of proof, but you base at least part of the proof on figures. Say, for example, that you have these square numbers, like you put dots or balls in a figure like this. Then you say that, okay, this is 1, 3, then you can add 5 and add 7. So if you take the square of 2, square of 3, square of 4, you say that the same thing as adding here 3 balls, then 5 balls, and 7 balls. Then you just maybe generalize this to say that this proves that the next one will be 9 and 11, that these will be all the odd numbers. So something like this basing on a figure that it proves. So strictly seen, a mathematician's research level wouldn't accept just basing on figures like this, but in school you could accept it at least as motivation for proof. And then we can talk about intuitive proof. And this is, just we showed it was some kind of intuitive proof. That is more like a proof sketch and a convincing argument, logical argument, instead of a strict proof. So for example, in a soon coming lecture, there will show that we argue that every integer can be written, or every natural number can be written as a quotient. And so if we divide a by b, then we can always find a quotient and a remainder like this. And the argument we give there is a kind of an intuitive proof, or sketch or motivation at least. So you can check your eye up in the corner there for that. Then we can also talk about examples example as proof. Examples or counterexamples. And what do I mean by that? Yeah, for example, if I claim that there are that if you add, like say here for example, if I add two even numbers, they will always be an even number, the sum. But let's say that I could find a proof, example that didn't hold. For example, now it's a silly example because it doesn't work. But let's say I found that 8 and 12 suddenly made an odd number. Then this example will prove that this to be wrong. So if I want to prove this wrong, I can just find one example, and that would prove that it was wrong. Then I found a counter example to that claim, that every sum of two even numbers is even. Or another example, let's say that I have the following statement or proposition in mathematics, that there exist natural numbers so that this holds. So this could be, let's say there's a claim, mathematical claim, okay, there exist integers I could put here to make this true. And then I can just find an example that will prove that statement, because it says it only exists. It doesn't say I have to prove it for infinite many or something. And for example, here I could just take, as an example, 3, 4, and 5, because 3 squared plus 4 squared equals to 5 squared. And this example proves this to be true. But in general, you can't just give an example of a proof. For example, up here, that we want to show that the sum of two even numbers was even. Then you can't just say, okay, 4, 6, and 8 is 14. So it holds there, and then give 10 examples, and then expect that to be proof. No, that's not proof. But this is of another type. Here the claim is that they exist. And then, of course, you just have to find one to prove that. Or you can talk about indirect proofs. Or you can also call it proof by contradiction. And then you want to claim something, then you want to prove something. Then you could assume, for say I want to prove that x is true. Then I could assume that, let's say that the opposite is true, and then show that something unreasonable follows from that assumption. So for example, let's say I wanted to prove that n squared, if this is an even number, then I want to prove that then n is an even number. Okay, so let's say I want to prove this. Okay, so how could I prove that? I could, for example, assume here now that instead of proving it directly, let me assume then that n is odd. So let's say I assume the opposite of this, that n is odd. Then I could show that n squared must be odd. Then I have indirectly proven this, because if n is odd, then n squared is odd. Let's say I have proven this. Then I have indirectly proven this, because if n squared is even, okay, if n squared is even, then n can't be odd, because if it was odd, then n squared would be odd. So I have proven it by contradiction. So you prove something by assuming the opposite and showing that that leads to a contradiction or something that can't hold based on the assumption you have made. So we will see examples of that also later on. Then the final one we want to take up here. This is not the complete list of the types, but the list we will take up here. Induction proofs. Then you want to show things, for example, in number theory, induction proofs can be useful. For example, let's say that I want to show that all the triangle numbers. And what are the triangle numbers? Those numbers I can form as triangles like this. And so on. So this is 1, 3, and this is 6, and so on. So these are called triangle numbers. Let me say I want to show that the triangle numbers are given by this formula. That the mth triangle number I can find from this formula. Then I could use an induction proof, because this has to do with integers. And then I want to, without going into details here now, I want to prove, in induction proof I want to prove two things. I want to prove the formula true for some starting point, and usually the starting point here is 1. Okay, so I want to prove the formula true for one starting point. Okay, let me check if it's true for number 1. Then it will be like this, and that's correct because this is equal to 1. So the formula at least is correct for the first one. So that's the first thing I want to show. Then the second thing I want to show is if I assume that the formula is correct for one number, let's call it m, then I want to show that the formula is correct for the next number. So if I assume it's correct for one number, I want to show it correct for the next number. So if I can show that, if you can show these two, then I have proven it for all natural numbers. We won't go into details here, but I'm just sketching out here what the induction proof is. And this is quite common to use in number theory, for example. You want to prove things. And also in the foundations of mathematics. You build up the whole of mathematics. These types of induction proof are essential part.